Obinna, many years ago, was a PhD student in Cape Town. And then you went on to postdoc in Portsmouth, after postdocs actually also in Cape Town at the University of Western Cape. And he's going to tell us about obtaining smooth distances from a lumpy universe. So, off you go.
Yeah, thank you so much, Chris, for the introduction. Yeah, Chris was my boss for about 3 years. And yeah, so I'm happy to talk about these papers that came out recently. And some of the results there were things that we encountered during my PhD. Can you hear me fine?
We might just need to play with the volume at our end. Sorry, we've got a new bit of kit. Is that where it's coming out? I don't know.
It's coming from.
No,
It popped up.
did it? Can we do that again?
Yeah.
Should I do the lights?
Okay, can you hear me now?
Yes.
Okay, yeah. Yeah, thanks. As I was saying, that I will talk about the first 3 papers and the one that is yet to be completed. In fact, most of the results that I would show would be sort of an update on the results that have already appeared. So when these papers appeared on the archives, I received a lot of emails, some angry emails, some very comforting, some were asking some questions that needed further clarification. So my plan was there will be a paper that would be out. I had plans to put it on the archives in May, but a lot of things are happening. So I couldn't accomplish that. So you would, be exposed to the result that would appear on the archives very soon. And I would be happy if you do not understand most of the things that I'll be talking about, you can stop me at any point. As I mentioned earlier, this is something that I've worked on for so many years. Sort of, I can claim that we predicted the Hubble tension before it became a thing. So, I mentioned the motivation for this work is the current Hubble tension, or the cosmological tension in general. Hubble tension is just an example of it. There will be more tensions to come. So what it is all about is I've taken this figure from a review paper that appeared, I think, in 2020, that summarized what the tension is all about. It is about the early universe observations that infers the Hubble rate using the Friedmann-Robertson Walker space-time. And the value of the Hubble rate that they get is the one that appears on this purple line here. It's smaller than what you would get if you go out there and count supernova or measure supernova magnitudes, then calibrate them to infer the Hubble rate. When you do that, or in general, all the direct measurement, when you use direct measurement approach to infer the Hubble rate, so in principle, you are not assuming a specific space-time or model, the value you would get will be slightly greater than what you would get from the early universe observation that uses the Friedmann-Robertson Walker space-time. And that difference recently has been shown to be around 5 sigma. So it is a real tension that wouldn't go away without an explanation. And the explanations that has come up is purely what you would expect from cosmologists that love the Friedmann-Robertson Walker space-time. So the first thing that they do is to keep the Friedmann-Robertson Walker space-time and try to alter the right-hand side of the Einstein field equation. So when you do this, you wind up with different models that have appeared. An example is the early universe dark energy model. The early universe is trying to sort of alter the distance measured at the early time, then they claim that when you do that, you can reasonably explain away the Hubble tension. There are other models that are sort of contrived. It's called the late dark energy model. The late dark energy model tried to change the behavior of dark energy at late time. But these models had encountered a big obstacle that I would explain that in detail later, that they can explain the H0 tension, but they cannot explain where the absolute magnitude of the supernova came from. So the other option would be to change the metric answer. So you abandon Friedman, Roberts, and Walker. Maybe you choose the LTB. So when you do this, you will require a big void. You will require that we live in a big void in order to reconcile the H0. The other option, which hasn't been successful, I think, is to modify gravity in general, just to modify gravity and hope to find a solution. So what I'm going to talk about is like trying to build up the microscopic, try to build up a space-time from microscopic information. So basically, I will start from a lumpy, inhomogeneous space-time and try to recover the smooth Friedman-Robertson Walker that sort of explains the universe on very large scales. So that's the approach I'm taking. And this approach does not involve, it's not like doing the book type averaging, no. So basically, I'm going to be calculating the observables, things that we measure in an inhomogeneous space-time. Instead of calculating them on a Friedman space-time, I take a space-time that has inhomogeneity, but is very close to the Friedman. So the observables in question are, or what we really measure, is in the case of the supernovae, is the apparent magnitude. Because the apparent magnitude, you measure them is meaningless unless you calibrate them. So the key, one thing I'll be mentioning a lot of times later here is the absolute magnitude. It's very key to extracting information from the apparent magnitude of the supernovae. So the other thing to note that have made that the absolute magnitude is usually defined as the flux when you measure that at a distance of 1 megaparsecs. This is important. Then the other observables is in the case of the galaxy redshift survey is the standard, the BAO as the standard ruler, because the BAO, the physics of the BAO would help you constrain this length scale here. But the way the information is extracted from the 2-point correlation function, or the information about cosmology is extracted from the 2-point correlation, is via what is called the Acog-Facinski parameters. So in principle, what you measure from the 2-point correlation function of the galaxy survey is the Acog-Facinski parameters. So this alpha parallel and the alpha pep. So you would need to assume a cosmological model to extract H0 information from here or here. So I will be focusing on these two things in the discussion that follows. So as you can see, the key quantity here is distances. For example, in the standard candle, you see that the apparent magnitude is dependent on the luminosity distance here. And if you look at the Acog-Facinski parameter, the key quantity here is also the area distance, this thing here. And I'm not the first person to calculate the area distance in an inhomogeneous universe setting. In fact, the group there at Queen Mary, they did a comprehensive work, I think, where they calculated this from a GR simulation. So they estimated the luminosity distance and different fractions of it. But for the talk that I'm going to be focusing on, what I'll be focusing on is the first two terms here, the luminosity distance and the square of the luminosity distance. So this square of the luminosity distance here is like a placeholder for the area of the screen space. So the calculation by the Queen Mary group, led by Julian, shows that the corrections, so the D bar here means the distance on a Friedman robotic Walker spacetime, while the D is from the inhomogeneous spacetime. So they computed the ratio here. You would see that at very low redshift, that the FRW spacetime is a fantastic model for the universe. But there is an issue here. If you if you don't work in this area, you may not know. The thing is that this simulation that they did, they cut off the redshift at about 0.02. And the motivation for that is based on this analysis by the choose group of the supernovae. So the choose group, where they actually infer cosmology is from the distance of greater than 90 megaparsecs away. Those were the supernovae that they used to infer cosmology. So this is what I've shown here in the third rung of this distance ladder. So the supernovae used for cosmology are those ones here. And this is about 90 megaparsecs away from the observer somewhere here. But that's not the full information, because as I mentioned here, you have the apparent magnitude, but apparent magnitude is useless without calibration. So choose group calibrates the apparent magnitude with the distance information from here. See, so here is the distance here is about less than 10 megaparsecs. So the geometric distance, so when I say geometric distance, I mean independent measure of distance that they use to calibrate the apparent magnitude of the supernova in the Hubble flow. So the Hubble flow is here, but the anchors, the distant anchors live here. They live very close nearby. So for example, one of the quantities that they use is the Cepheid in the Milky Way. Milky Way galaxies is just like few parsecs or kiloparsecs away from here. They also use the distance to LMC. So in this case, they're looking at the detached eclipse in binary in the LMC. So they use that to calibrate the supernova in the Hubble flow. Not directly, they use this information to calibrate the Cepheids that live in the same galaxies as the LMC. So once you calibrate the apparent magnitude of the Cepheids here, you can then use that to calibrate the apparent magnitude of the supernovae in the second rung here. So the supernova, the only condition is that supernova must live in the same galaxies as the Cepheids. So that's how the calibration goes. First of all, you calibrate the absolute magnitude of the supernova in the absolute magnitude of Cepheids in the first rung here, using independent geometric distance information. Having calibrated that, you can then calibrate the absolute magnitude of the supernovae that lives in the same galaxies as Cepheids here. Then once you have the absolute magnitude of the supernova here, you can then apply them to the supernova in the Hubble flow. That's how it works. So stopping the distance information here is incomplete, because the key information, the key parameter that goes into the calibration of the supernova in the Hubble flow is coming from here, the independent geometric distance anchor. So that's the way I'll be focusing. I will try to push the distances in the inhomogeneous, calculation of distances in the inhomogeneous universe down to these scales. So I've mentioned here, there is a historical, having this result here is not really unexpected because there is a historical conjecture by Weinberg, which says that if you impose photon number conservation, that the space-time of the universe, irrespective of scale, will be given by the Friedmann-Robertson Walker space-time. So this is the first thing that we will try to understand and see the loopholes that exist in that conjecture. So the conjecture is valid only when you understand all the loopholes there. So that's what we will go ahead to see now. So the one thing that we know is the flux. So the total flux coming from a source, say a point source, obeys the inverse distance law. So the flux is given by the intrinsic luminosity divided by 4 pi times the luminosity distance squared. So this is like the area. The flux falls as a function of the area. So I've given this a sphere here. Imagine you have a supernova at the center here. It goes wide. Then you put in a dictator somewhere here. With the dictator, you can count the number of photons that hit that dictator. So just simply based on that, we can come up with these two invariant equations. So the first one is, imagine the supernova is here, and the sphere is given by the Friedmann-Robertson Walker spacetime. So from the flux formula, you can work out, you can see that the area, the total area, or the total, the area of the sphere will be proportional to, or the number of flux you will get hitting the surface area of the sphere will be proportional to the area. And the same thing holds also for the dictator. If you put a dictator for a small portion here, the number of photons that will hit it is proportional to the area of the dictator or the telescope. So this holds. Then imagine that this sphere is replaced, you put in inhomogeneities. You can switch on gravity a little here. We have, this is no longer a Friedmann-Robertson Walker, but an inhomogeneous spacetime. You do not know the nature. This law will still hold. The number of photons you get, number of photons will be proportional to the area of the sphere, and the same thing for the dictator. The difference is from here is that you could have, this number would differ in this case. So the number would differ depending on the amount of inhomogeneity you have on the line of sight of the dictator. So what the Weinberg photon number conjecture is saying that if you look at this here, and you assume that you have large number of dictators put in around here, that in the large n limit of it, in fact, by the law of large numbers, that the mean will be proportional, will be given by the Friedmann-Robertson Walker spacetime. So in the large n limit, then or you can say on average, this number here will be given by the Friedmann-Robertson Walker spacetime. So this is the first statement, and there are criticisms of it. That one of them is from this paper by Mustafa Bassett and Helaby and George Ellis, where they say that if you average an inhomogeneous space-time, you don't recover the Friedmann. So the other thing here is that so this is where the Weinberg conjecture comes in. That if this law of large number holds, since the area of your telescope is fixed and a large n limit of it, you get Friedmann, this total number of photons is unchanged by photon number conservation. Therefore, the area on average would also be given by the Friedmann-Robertson Walker spacetime. So this is the photon number conservation / Friedman-Robertson-Walker space-time conjecture that I mentioned. This was criticized immensely by, in this paper by George Ellis, Bassett, and Downsby. So when you make this assertion that if you integrate this, there's a lot of assumptions that you have made. One of them is that you do not have any focal point or caustics. So your geodesics do not converge at any point when they move from the source to the observer. So what that means is that the determinant of this is non-zero at every point. And you know in cosmology that this isn't the case because we have strong lensing. Strong lensing is associated with caustic convergence. And also in the Weinberg paper, he really didn't pay more, or the follow-up papers, they always assume that the homogeneities here are randomly distributed. And we know that if we switch on gravity, it would impact how the clock ticks and your ruler. In fact, this was looked into by Kaiser and Peacock. They were able to calculate the corrections to the area due to gravity, sort of, yeah. And they found that the conclusion is that the effect is there, but it's very small. So the Weinberg conjecture holds, approximately holds. But this argument about the existence of focal point has not been sufficiently dealt with. So if you assume the Weinberg conjecture, this is what it means for cosmology. That if you average over flux or over the area, it will be given by the area or the Friedman-Robertson-Walker distance squared. This is a very concrete statement. And the magnification, if you average over magnification over the area, it will be proportional to 1 unity. So there's no relative magnification or demagnification due to inhomogeneity on average. Also, this was proved by Cable and Liu that the inverse of the magnification, if you average that over all sky, it will also give you 1. So remember, most of these proofs assume that the inhomogeneities are randomly distributed. And the area, if you take an average, if you take an all-sky average of the distance, luminosity distance, it will be given by this expression here. This is just the convergence, weak lensing convergence that you know about. So this term is only important at very high redshift, and the correction is very small. So at low redshift limit, the distance is given by the Friedman-Robertson-Walker spacetime. If the Weinberg conjecture holds, and also the source area or the source average would be given by this. The key lesson here is that at low redshift, the distance will be given by the Friedman-Robertson-Walker spacetime if Weinberg photon number conservation / FRW distance conjecture holds. This will be the result. But there was a paper also by George Ellis and Solomon in 1998, but no one actually paid attention to this, where George tried to give an example where this is not true, where the average of the area would not give you the Friedman-Robertson-Walker spacetime. In this case, he used a Swiss cheese construction. He showed that there is a radio component, a radio contribution to the area that doesn't vanish. And that's what is responsible. That contribution leads to an increase in the distance. So you have distance increases, you have sort of a demagnification. So this is with the paper they did in 1998, and nobody actually paid attention. It has 15 citations, and I contributed 2 to these citations. So most of I think the reason people didn't pay attention is that maybe it's the Swiss cheese. But in fact, it shows that there is a space-time where the Weinberg conjecture doesn't hold. So this is from this paper, you can read that in detail, but the radio lensing part, in fact, for the papers, as I would show later, that rediscovered Doppler lensing. Doppler lensing is just an example of the radio lensing here in a specific gauge. The papers that rediscovered it did not really pay attention to this paper or cite them, which is weird. So the point I'll be talking about is how to actually compute this radio lensing contribution in a standard perturbed Friedman-Robertson Walker spacetime and what it is. So this is what it is. The one important thing you should notice about us is that we live in a local group. So in a cluster called a local group. So it is a galaxy cluster, sort of an overdensity. And we move with a non-zero relative velocity with respect to the cosmic press frame. Or even if we do not mention the cosmic press frame, or within our own solar system here, we move around the sun. So we have an overdensity sort of the sun. And the distances we measure of the background sources, because we move around, we would always tend to infer the position of sources, of background sources, with respect to our velocity or where we are at the point that we make that measurement. So the typical example I'm giving, the way that actually compute that here is that if you live in an overdensity and you want to infer the position of a source far away from you, you would sort of infer the position here, where in actual fact, the source is somewhere here. Because you live in an overdensity, when light tries to get to you, it's deviated by the overdensity that you live in. And you can actually compute this. You can calculate the deviation, the change in perturbation theory. Because my calculation is in perturbation theory, I have freedom to do a lot of things. So I can define the deviation vector this way. So this is what is called the reduced deviation vector, because I'm normalizing it by the area distance. I have sort of an invariant measure. And I can define the area this way, just the determinant of the Jacobian of the transformation from this, let's say, Friedman spacetime to a perturbed, and it's given by this. So when you try to decompose this, there's a paper by Fabian Schmidt that actually shows how to do this. If you want to look at it in detail, you can decompose the Jacobian, and there is this extra term that would appear. This extra term, people that have looked at the area, have computed the area before, they usually do not pay attention to this term. So, but when you decompose, this term would appear. And this term is associated with the radio lensing that I'm talking about. So it's coming from the fact that the line of sight actually converges or starts from the observer, then diverges away, and is given by this. But you can still recover what we call the weak lensing convergence in this form with a small distortion, if you like. So the distortion is only happening to the gravitational convergence. So this kappa S, I'm written kappa sub X. So in general, this is what it is. It has two components. One is due to the radio lensing, and the other one is due to the tangential, so the distortion that happens tangentially. Most of the work in this area has focused on this tangential component. It was recently that people are beginning to pay attention to the radio component, but none has actually calculated the area distance, including this tangential component. this radio lensing component. So when you compute the area, it will be given by this. See that the radio lensing terms appear. We compute the area distance, it appears as well. So on a perturbed spacetime, in a general perturbed spacetime, this is the radio lensing contribution is given by this. So, but this is the affine parameter. This lambda here is the affine parameter. It's not measurable. You would like to at least relate your area distance in terms of what is measured. For example, what we measure is the redshift of a source. So the redshift of a source is a combination of so many things. One is it includes the expansion of the space-time, the first thing you see here, 1 plus z bar. So it describes the cosmological expansion. So the expansion of the space-time. Then you have additional contribution. This is a contribution due to, because in this case, we are heliocentric observers. So we are sort of in the frame of the sun. So this observer, this is our perspective, this is our view of the world. It's coming from we moving. Although we move, we have the Earth moves relative to the sun. That contribution is known, is always calculated and subtracted off. But our view of the universe is from the perspective of a heliocentric observer. Also, the source we are looking at is also moving with its own peculiar velocity with respect to the cosmic rest frame. And you know, the redshift is related to peculiar velocity in this way. And what I will be focusing more on is purely our own velocity, because that's what appears in the computation of a distance. For a heliocentric observer, the peculiar velocity is sort of a combination of so many things. So you have a velocity that describes how the sun is moving with respect to the local stellar system. Then you also have the stellar systems within our galaxy moving relative to the galaxy center. And you have our galaxy also moving relative to the center of the local group, our local group. Then our local group is also moving with the relative velocity with respect to the cosmic rest frame. So these are sort of different velocity contributions to the heliocentric proper motion. So in this case, so I've mentioned that we are heliocentric observer. This is what we want to calculate. But my perturbation theory tools is not valid on this scale of the galaxy dynamics, even internal local group dynamics. I will go into detail on how to determine this because of the group, QMUL group. You work on something similar to this. So in what I will be calculating, I would calculate things from the perspective of a fictitious local group barycentric observer. Sort of, in reality, I will only be calculating the relative motion between the local group or an observer at the barycenter of a local group with respect to the cosmic rest frame. There's a way to handle that. I will show you right now. But I will show you how to determine where your perturbation theory breaks down. I'm doing this because there's a recent paper by your group that I find very interesting. It sort of converged or is in agreement with what I've found in qualitative agreement. So this part of computation is like is a topic in the mathematical study of singularities. Basically, I'll be looking at, if you want to understand better what this is, you can look at the book by Hawking and Ellis. Basically, what it is that if you have 2 points in a manifold, how do you determine causality to how do the 2 points communicate with each other? So basically, what you do, the points here, Q and point P, what you do is you vary you have a set of curves starting from Q, moving to P. then these curves are parameterized by one parameter. So this is important. These curves are one parameter family of curves, moving from Q to P. If you vary an action to this, you obtain the geodesic. The second variation will give you the Jacobi equation or no or geodesic deviation equation. So it's given by this. And one thing unique about this, it has a unique initial conditions. So it starts from here and here. And so these are further complications. If you're not familiar with this, but don't worry. The key thing that I will mention going forward is this term here and this theta here. So this theta here tells you how these curves are converging or diverging away. So, yeah. And in the singularity theory paper, a curve converges where, like for example, here, if you have a set of curves starting from a hypersurface and converges at a point P in the future, and the point where it converges, there are two conditions for converging. One is when the 1 over theta, this is capital theta, where this term goes to 0. So where theta goes to infinity. So this is a classical singularity theory argument. But the other one that is more precious to us, cosmology, is in the other condition where theta actually goes to 0. So in the case where theta goes to 0, this happens in the real universe because theta, if you write it down in an expanding universe, it has two contributions. One is what I've called theta H and the other one theta L. The theta H is the Hubble expansion part. It's given by 3H. While the other part is just of a divergence of the relative velocity. So there are locations in the universe where this theta goes to 0 or where this is proportional to minus this. So, and these surfaces can actually be observationally constrained. They are called the zeroth velocity surface, where theta goes to 0. You see that in locations where theta goes to 0, the volume is proportional to the initial volume, and the initial volume for the initial condition here is typically 0. Whenever this happens, from the differential geometry point of view, it means that the coordinate system induced by your geodesics breaks down at this point. It's called the conjugate point. So in the universe, you have these conjugate points. In this case, I've only focused on the timeline geodesics. You can make this argument for the null geodesics. You have that you have these conjugate points before any observer. So the space-time, assuming you started with what I've started with, a Friedmann-Robertson Walker space-time with some perturbations on it, you can't cover the entire universe with that same coordinate system. It breaks down at a certain point, and you can quantify them or measure them observation. You can quantify them if you like by calculating this explicitly using the NFW profile. You can show where this condition is satisfied. The observational constraint that I found is around 1 megaparsecs. And the group, Queen Mary, you did similar computation. You have this type of plot in one of your recent papers. And I think where we disagree is on the number here. So this number here is observationally constrained, that is happening at 1 megaparsecs. So the space-time, the expanding coordinate system that cosmology is based, breaks down at 1 megaparsecs. So my perturbation theory treatment, I cannot push it beyond that point. One way to go beyond, because I showed you that some of the anchors, distance anchors that the Schultz group uses are very much close by, like Cepheus in the Milky Way. I can't describe them using perturbation theory framework. Secondly, I can't describe distance to LMC. It's about 4 kiloparsecs away. It's less than 1 megaparsecs. I can't describe them with my perturbation theory group. approach because it breaks down around here. So the only thing I can describe from the choose group is the distance to NGC 4258. NGC 4258 is around 7.5 megaparsecs away. So my talk, what I'm calculating is specific to NGC 4258. Then, yeah. So in that case, I told you I positioned the observer at the barycentric center, then to express my result in terms of the cosmological redshift. This is how you do it. It's a technical stuff, but you set the perturbations to 0. That defines the constant redshift surface. This is important. For cosmology, you need to be in a constant redshift surface. Otherwise, there's the paper by the Oxford group that shows that if you compute these things in the heliocentric redshift frame, there's a marginal evidence for dark energy, if you like, and you wouldn't even have this Hubble tension you're talking about. So the Hubble tension is only obtainable if you are in a constant redshift frame. So that is really important. We have to express this result in that frame. So if you write your radio lensing contribution, you have this. So the key contribution is coming from this term I've identified in red. And you compute the monopole of the area at fixed redshift is given by this term. And at low, for the distance, you would have a correction. So what that means is that your FRW distances is modified at low redshift by the impact of radio lensing or Doppler lensing. So now that we are in the conformal Newtonian gauge, we can confidently call it Doppler lensing. So because we have introduced peculiar velocity. So there is also something to note here. So if you compute this at, if you compute the monopole, this first time here will drop out, will average to 0. There's a reason for that. So the contribution is actually coming from this term. With respect to our local group barycentric observer. But if you are interested in heliocentric observer, this is what is done for the CMB. What you do is to expand everything in spherical harmonics and drop the first two terms, L equal to 0 and then L equal to 1. These two contributions are coordinate dependent. Then you sum over the rest. So at the end of the day, you now boost back to the correct frame to get the accurate answer. This is how it is done for the CMB. And when you do this calculation, you calculate the first line. This is what it is in the spherical harmonics. If you're interested, we can come back to discuss this in detail. I see I'm running out of time. So this is what you get. You start summing from L equal to 2. And there's a mathematical proof for this. If you like, we can show this. All you need is the Peyranes proof that the STF tensor is proportional to spherical harmonics. This correspondence, we can show that L equal to 0 and L equal to 1 can be removed by coordinate transformation. Then once you have this, you can calculate the corrections that I'm talking about. For example, the area. You see that, I'm only focusing on very small redshift. Because if you go far away at high redshift, the Friedman-Robertson Walker predictions is valid. But on small redshifts, this is where NGC 4258 is. You see that distance to it has a correction about 5%. It's small, but it's non-vanishing. That is not where the key effect is coming from. Then this is the area you have descending. So I have indicated Z cut here. So the Z cut I've indicated here is proportional to where I showed you that my space-time or my perturbation theory techniques breaks down. So this is where my perturbation theory breaks down. Beyond this, I can calculate the distances. So this is like a distance of 7 megaparsecs away for NGC 4258. So what does this mean for the cosmological tension? This is where it gets more interesting, because what we measure is magnitude. And magnitude is a function of so many things. You have a transmission function of the bandpass and all the corrections. But it is given by this CB over CB to the power 0. This is the fundamental flux, or fundamental sort of photon to compare your apparent magnitude of any source to. This fundamental frame sort of does not exist. In the case of the supernova, what they do, as I've talked about before, is to compare to known secondaries. So you use an independent distance anchor to calibrate this flux here. So when, for example, Cepheids, and you compute this with respect to known Cepheids apparent magnitude. You can compute this with respect to known TRGB apparent magnitude. So these sources, as you can see, is a flux. Flux is a function of distance. They could be at different distances. So you need to sort of a standardization. So the standardization for cosmology is that you compute them with respect to the flux, their prediction for the flux at 1 megaparsecs. So that's the prediction for the flux at 1 megaparsecs. That's how you get the distance modulus. So that's the definition of a distance modulus. And with respect to the choose calibration, the way they do that, I will run through how they do it. So you need the absolute magnitude of the supernovae in the Hubble flow. And you compute that by looking at the supernovae in the second rung here that has a Cepheid counterpart. So this is the distance modulus to the Cepheid in the second rung here. And this distance modulus, if you put it in back here, you see that you have to also calibrate its apparent magnitude. Its apparent magnitude is defined as the Cepheid. You have to calibrate its absolute magnitude. The absolute magnitude of Cepheids is defined as its apparent magnitude measured at a period of 60 days or 60 minutes. There's the standard definition with the dust correction set to the solar equivalent. So the apparent magnitude here for the Cepheids is determined purely from independent distance information. In this case, is the distance to the NGC 4258 obtained by measuring the Mesa profile produced by the supermassive black hole at its center. So from there, you can get the estimate for this distance. So that's what I've shown here. And this is also a figure from the SHUS group, what they do. So I've mentioned the first one is that they calibrate using the Milky Way Cepheids, and calibrate using NGC 4258, the mesas in the NGC 4258, and also detach the eclipse in binary in large Magellanic cloud. But my computation is purely with respect to NGC 4258. That's the one I can compute within perturbation theory. Then, I've calculated this in an inhomogeneous space-time. You sort of have to interpret what it means. And the interpretation sort of is following this sort of cosmological fitting problem proposed by George Ellis and W. Stoker. So the point is that you take the Friedmann-Robertson work as space-time to be a pragmatic model of the universe. You know that it has three parameters, but those three parameters would be fixed, or they would be fixed in the presence of inhomogeneity. So that's basically what I've set out here. So you have a Friedmann-Robertson work at space-time, which will have a metric, you have observers there, we can compute all these things there. But you have a representative model, a model that tends to capture the inhomogeneities in the universe. That's what I've calculated that model using a perturbed Friedman spacetime. Within that model, I can compute also the apparent magnitude, Acog-Facinski parameters, and all these things. Then the way I interpret my model with respect to Friedman is to take the all-sky average and compare the two results. So that's basically what then that will help me determine the best fit parameter for the universe. So the first thing that I would like to resolve is what is called the supernova absolute magnitude tension. It was sort of defined in this way in this paper. So what it is all about is that the apparent magnitude, the absolute magnitude of the supernova in the Hubble flow, that's this column I'm pointing out, determined by local measurement. So the first one I have NGC 4258, Milky Way Cepheus, and the LMC. Then compared to what you would predict for them, if you use the FRW space-time and Planck cosmology, this is what you would predict. Then the difference between them is given by this. This difference is called the supernova absolute magnitude tension. Is another way to rephrase the Hubble tension, the tension in the Hubble rate. We can rephrase it in terms of the tension in the absolute magnitude. So this is what I've calculated by including what is now called the Doppler lensing. So I'm calculating the difference between, this is what inhomogeneous spacetime would give you, and this is what Friedman-Robertson Walker will give you. So the difference here, especially, is just what I've defined here. If you calculate this, the magnitude, and determined at 1 megaparsecs, that's where you define the absolute magnitude. We see that the difference you would get is 0.11 magnitude, which if you look at the first line here, the NGC 4258, this is what you get here. So including the inhomogeneity here, you resolve the supernova absolute magnitude tension. Then the other thing is the Hubble and the BAO, where they made the observables are the Acog-Facinski parameters that I've defined earlier. So in this case, if you replace these distances with the perturbed version, you can calculate and show that the correction here is given by this. And you can expand this in spherical harmonics, and you get this. But remember that my perturbation theory breaks down at about Z coord. But if I pretend that I can analytically continue that to Z equal to 0, I can determine the H naught here. And the correction is within 0 to 14%, depending on the scale where the perturbation theory breaks down. So, and it is around 1 megaparsecs here. So that immediately gives you the calculated tension in the Hubble rate. So that's the conclusion. So this I would conclude here, so we have more time for questions. The background FRW spacetime does not give the correct distance estimate in the universe at all times, especially at low redshift, very low redshift. You have corrections due to inhomogeneities or due to Doppler lensing or radio lensing. So my claim, or what I've showed, is the early universe tension is due to this. It's probably due to this. Let me not be more assertive. Then there is something I think I mentioned it, but I haven't calculated it, is that my perturbation theory breaks down at a point. So I need to use sort of non-perturbative approach, or in your group, a two-parameter perturbation theory to take into account the proper motion and due to our heliocentric system. So that's the missing link here. I need to include the proper motion. I need to boost to heliocentric frame and be able to calculate, in addition to that, be able to calculate distances to the LMC and distances to the Milky Way Cepheus. And thank you so much for listening.